If A is invertible and AB equal to AC, prove quickly that B equals C. Okay. Let me show you why, Ben. This is true. Let me help you out. So for part A, if so, the question is saying if A is invertible, prove that. Now with matrices, unlike algebra, you can't just say if 5x equal 5y, you can't just cross out the 5. In algebra, you could cross out the 5 and say x equals y. Well, in matrices, it doesn't work that way because this guy A is actually a matrix. So then AB, so these are all matrices, equal AC. And the way you could prove that is you can pre-multiply both sides by A inverse. And look what happens when you do that. So A inverse, and here I'm gonna multiply on A inverse. Order matters here because with matrices, matrix A times matrix B does not necessarily equal matrix B times matrix A.
Yeah, I get that.
So here you have A. Okay, watch. So A equals C. Okay, now what's this here? A inverse times A. This is the identity matrix times B, matrix B equal. Same thing here. A inverse times A is the identity matrix times C. Now, when you multiply any matrix by the identity matrix, you get the matrix back. That's what the identity matrix mean. And so this product here will just be matrix B, and this product here will be just matrix C, and therefore we've proved that those two have to be the same. Now, the reason that it has to be invertible is precisely because of what I did. Had A not been invertible, I couldn't multiply by A inverse because there wouldn't be an A inverse to pre-multiply with in the first place. That's why A needs to be invertible for me to do this pre-multiplication step.
The identity matrix multiplied by a matrix should be the identity gives you the diagonal of the other matrix, not the original matrix.
No, the identity gets you the original matrix. Try it out. If you pre-multiply or post-multiply any matrix by the identity matrix, you get the original matrix back. That's what the identity matrix does. This part B captures exactly that idea. It says A equal 1, 1, 1, 1. Find two different matrices where these are equal. Notice that matrix A is singular, meaning it's not invertible because the determinant is 0 here. 1 times 1 is minus 1 times 1 is 0. So that means you could possibly find two that are different where you still get AB equal AC. So let's go ahead and do it, and you'll see where how that fails. That what you're gonna end up with is two non-necessarily equal matrices. Okay, so for part B, let's see how this will work out. How we will be able to find two different matrices where AB equals AC if A is not invertible. So we have AB equal AC. This is the condition we need. These are all matrices, of course. I could move AC to the left. At this point, I'll stop putting these dashes just to save time. We know that all these are matrices. So then AB minus AC equals 0, matrix. This is a matrix, of course. And now I could factor out A, and I would get matrix B minus matrix C has to equal 0. Now that means either this has to equal 0 or the difference between the two matrices equals 0. Now since the question claims that I need to find two different matrices, it can't be that B minus C equals 0 because this cannot be 0. Otherwise, if this equals 0, then B equals C, and that's not what I'm trying to find. So that cannot equal 0. Okay, so now we need A. So let's just say that B minus C has to equal it can't equal 0, but keep in mind that I'm supposed to multiply A by that and get 0. So I have here 1 1 1 1 times B minus C, and this is supposed to get me 0. Okay, so let's see what we can make out for B and C. So so here I have 1 1 1 1. Okay, let's see, well, how do I get 0 here? Well, sorry, there's a multiplication. Okay, so how about let's say I call this X and Y, right? What will I get here? Well, I will get, so I need this first entry here to be a 0 to get a 0 matrix. So let's fill in. So row matrix multiplication goes row column. So X, which means this guy here has to be minus X, right? So that it goes away to 0. So I need to make minus X here so that I can get a 0 here. So X minus X is 0. Okay, likewise here. So this is going to get me Y. What do I need here to get a 0? Well, I need minus Y, so that this guy here will get me a 0. Now, does it work on the other column? Well, it has to, because I mean on the other row it has to, because it's the same row, 1 1. So I will still get 0 0. Okay, bingo. So now, having done this backward manipulation, I know that this is B minus C. Okay, so now the question is, what are two different matrices where when I subtract them I would get X Y minus X minus Y, that are different, of course. Okay, now here it's easy to come up with some answers clearly. So so let's go ahead and do that. So we have a 2 by 2 minus a 2 by 2. They're supposed to be different, and I'm supposed to get XY minus X minus Y here. Okay, well, you can think of many different combinations here. I could have 0 0 here, minus, and I could put here, right? So now I'm filling this in. Let me use different color to fill them in. So I need these to be X and Y. So if I put 0 here, how would I get an X there? I would put a minus X here. And I could put a if I want, I could put a 1 here, and then how would I get Y there? Well, then this has to be oh, but wait 1 second, X B minus C, yeah, XY minus, yeah. So I could have I need to get a Y. So if I put a minus Y here, I get plus Y, and if I put a plus 1, I would get a minus 1, and this guy would go away. So that's really simple, and you could do this variation for all the cells. Now here I need a minus X, so I could put a minus X here, and I could put a 0 here. Minus X minus 0 will get me minus X, and I could put a Y here, minus Y, so I can get minus Y on this, and I could put a 0 here. So so one of the ways is B, matrix B can be the first one, 0 1 minus X minus Y, where those could be anything, and C will be the second one, will be minus X minus Y plus 1, and 0 and 0 0. So let's see, does this work? So 0 minus X gets me wait, sorry, this is minus X. So 0 minus X gets me X. 1 minus Y plus Y, minus 1 goes away. Minus X minus 0 gets me minus X, and minus Y minus 0 gets me minus Y. So those are two different matrices. They're not the same. Where AB equal AC, where you would get AB equal AC in the event that A does not have an inverse. This does it.